All right, this is an AP problem. I think it's 2002 from the AP Physics C test. And I thought I would do this for just a good example of some things to study for on the test. So let me get my pen working here. All right, the cart shown above is made of a block of mass M and four solid rubber tires, each of mass M/4 and a radius of R. Each tire may be considered to be a disk, which is 1/2 mr squared, or they say 1/2 ml squared, or L is the radius of the disk. The cart is released from rest and rolls without slipping from the top of an incline height h. Express everything in terms of given quantities and fundamental constants. Determine the rotational inertia of the tires. All right, so A is I equals the sum of the mr squared. Well, for one tire, that would be M/4 times R squared. But how many of those tires do we have? We have 4 of those. Is that right? And I just messed up here. Hold on a minute. We already know it's 1/2 mr squared, right? So it's actually going to be 1/2 M/4. We know that because they gave it to us right here. I just missed out on that when I first did it. It's times R squared. And then how many of those do we have is the question. We have 4 tires altogether. So that's going to give me a total rotational inertia for all 4 tires of 1/2 mr squared. All right, so that's a pretty simple, as long as you remember to use 1/2 ml squared for each tire. So each tire is 1/2 M/4 R squared, and then times 4. So really, we didn't really have to have this, except for the fact that there's 4 of them. We would add them together, which is the same as multiplied by 4. So that's how you find the rotational inertia. B, it says determine the speed of the cart. All right, well, we know that it starts out with an initial potential energy and it ends up with a final kinetic. What we got to remember is that kinetic consists of 2 parts, a linear kinetic, we'll call that translational, plus a rotational kinetic. Both of those added together are going to give me my total kinetic, which is going to be equal to the total potential. So here is what we got to do. It's going to be mgh. Well, we know it's 2m. Why? Because it's a block of mass m, but then there's 4 tires that are M/4, so there's twice. It's 2m. So 2mgh equals 1/2 2m v squared plus 1/2 I omega squared. All right, so if we just work through here, let's work this out. 2mgh equals, those 2's are going to cancel out, so it's going to be mv squared plus 1/2 times, this is I now, I'm going to write I out here, 1/2 mr squared times v squared over r squared. All right, so this r divides out with that r, and then 1/2 times 1/2 is a 4, so we end up with 2mgh equals mv squared plus 1/4 mv squared, and that's going to equal what, 5/4? Yeah, 5/4 mv squared. Extend the page a little bit. So now what I'm going to do is I notice that my m's all divide out, right? So m's are gone. I don't have to worry about those. So when I move this over here, it's going to be 8/5 gh equals v squared, and so v is going to equal the square root of 8/5 gh. And if you look at the answers, sure enough, that is the total velocity as it gets to this point right there. All right. C, it says after rolling down across horizontal, it collides with a bumper of negligible mass is attached to an ideal spring. Ideal spring means that no energy is lost, so it can be considered an elastic collision. Spring has a spring constant of K. We want to know how far it is compressed. So if we do that, how much energy do I start out with? Well, I start out with 2, and this is C. I start out with 2 mg, and how much mgh, 2 mgh, how much energy do I end up with? Well, I end up with all potential spring, that's 1/2 kx squared, where x is going to be the maximum distance that it stretches, all right, or compresses in this case. So if I do that, then I get 4 mgh over k equals x squared, or x equals the square root of 4 mgh over k, which would be 2 mgh over k. And that's going to be my answer for how far, or the maximum compression of that spring. Okay, that's C. Now D says now we're going to assume that this bumper, which is the little flat part here, does have mass. Well, now it only compresses 90%. In other words, take 90% of this, and so there's 10% missing. What happens? Well, what you got to realize, if we put mass, this is an ideal spring, but if we put mass here, now we have an inelastic collision, so kinetic energy is not conserved in this crash. So that means when we're doing our conservation of energy, K is smaller because some of it's left the system as heat or whatever. That means that the potential spring energy is also less. So that's because it's an inelastic. Oh boy, I didn't spell that right. It's an inelastic collision. That's why. So that's an example of an AP problem.